Actually, this never was Yorick or anybody else come to that, because it isn't real. It's plastic. But it's still useful. Real skulls cost rather more and are difficult to get, but a student can learn quite a lot from one like this, as long as it's an accurate model of the real thing. And that applies to any kind of model, even the sort children play with. You can learn quite a lot about aerodynamics from a paper aeroplane like this one. And that applies to models on computers too. They're really only ways for the computer to play. Let's pretend.
Wind's calm, it's awfully bumpy up here. Gusty, I'll stay above the...
Engine fire on 1.
Confirmed, fire drill.
Bell cancelled.
Bring back to number 1. Fuel cock shut. Bravo Delta has number 1 engine fire coming straight in.
Bravo Delta, you are cleared for landing. Emergency service will be alerted.
I have trouser discharge, number 1, fire persisting.
Bottle discharged.
Well, if that looked as realistic to you as it felt to me, that's because we are in a simulator. We're not actually in the air at all. Well, we are slightly. We're about 10 feet off the ground in a rediffusion simulator in Crawley Industrial Estate. But these simulators have now become so realistic that some airline pilots around the world are converting from one type of jet to another without once stepping foot in an expensive real plane. They're doing it all from one of these machines. Alan, thank you very much. Would you like us to, could we pick up where we left off without too much danger to ourselves?
Okay, unfreeze, Bravo Delta confirmed, and we're clear to land.
Bravo Delta clear.
Take the controls.
I have control.
Whew, done it. Not the most perfect landing. Thank goodness it wasn't a real Boeing 727. And that's where we were, up in that box on legs. And those 4 protrusions on the front are the screens showing the lights of the runway. The hydraulic movements of the legs are not random, but designed to give the pilot and crew that final, almost sinister touch of realism. Even the bumpiest of conditions can be simulated. This is what a landing looks like from the outside. I hope his is better than mine. Tipping the whole thing forward gives the effect of putting the brakes on after touchdown. Quite extraordinary. Well, here, of course, is the very heart of the simulator, and you guessed it, it's a computer. It takes all the input fed to it from the flight deck, all the controls, and reproduces them as movements on the legs. The whole thing goes up and down. It reproduces them as changes in the dials on the flight deck control panel. And, of course, it produces those marvelous graphics that the pilot sees through the windows of the aircraft. In fact, it's about as close as it's possible to get to real flying.
I don't know, and nobody else has either, what the game of chess was originally designed to do. But it's not unreasonable to suppose that it was played by young aspiring noblemen in the East to train and accustom them to the complexities of medieval power politics. Well, if that was the case, perhaps it's interesting to look at the functions of the pieces and find out what aspects of the real world were reflected in their rules. But take the Queen, for example. She's the most powerful piece on the board, able to make great swoops in any direction and kill instantly. Bang. And conversely, if lost when a cluster of lesser pieces gang up on her, it's a calamity and inflicts great loss of morale. But the king is a different character altogether. He's dignified, he moves within his small area, in small steps, and he does no harm to any other piece unless he's attacked. Bang. The knight, he's a strange character. He seems most mercurial, he can zoom around the board in rather unpredictable steps, and of course he can can't be blocked by any other single piece. And the pawns, the peasants, the poor bloody infantry, relentlessly driven forward, never allowed to retreat, even if it means being taken. They hardly noticed or miss when they fall. But if, by some act of bravery or a cunningly devised plot, they manage to reach the other edge of the board, then they become automatically members of the aristocracy. Well, the interest and the difficulty of chess doesn't just arise from the rules governing how each individual piece can move, but from the interplay amongst the pieces and the almost infinite number of patterns and relationships between them. And you certainly can't get their full flavour by playing just one game. It's only after many you can start to judge how accurate a model it is and how well its rules reflect what's happening in the real world.
Of course, there are lots of games, and they certainly don't all represent aspects of the real world. Noughts and crosses, for example, is purely abstract, so is bridge, for that matter. But when we come to games like Monopoly or Snakes and Ladders, I suppose, there are at least some aspects of life which are being simulated. And simulation is the basis for many of the most popular computer games. Here's one, for example. It's a moon landing game. And with this joystick, you can actually try and get yourself and your crew safely down to the moon's surface. There's a little landing patch you're aiming for. You have a whole dashboard full of dials here telling you how far you've got to go, what speed you're going, downwards and that way. Now, gently, oh dear, so too far, it always happens. I've yet to land this thing properly. Down you go. Go on, chaps. Yes, same old story. Oh well. Part of the fun of a game like this is its closeness to the real thing. You really do have to watch your fuel consumption and get your height and spot exactly right to get down in one piece. It actually says, what a terrible landing. Another go, question mark. Well, no, thank you. In principle, it's really not very different, except in scale, from the big Boeing flight simulator. What's missing, of course, is the total realism. But a simulation doesn't have to model every aspect of the real world to be useful. Here's another example. Perfectly ordinary ball. And this is the computer's version of it. It's only a white dot on the screen, but it is behaving like a bouncing ball. And although we don't know how big it really is, or what colour it is, or who dropped it and why, if we wanted to know what happens when a real ball falls to a real surface, this simulation could give us an answer. In fact, what you have to decide with any computer model is which bits of information you have to get right to make it useful. It doesn't even need to look like the real thing, does it, Mac?
No, it doesn't. In fact, some models don't look anything like what they're supposed to represent. And I think we're all familiar with that sort of thing, which is, in fact, a molecule of cellulose. Yeah. And obviously a molecule of cellulose doesn't look anything like this, these balls representing the atoms. But the connections are correct, and it does give some sort of representation. And you can rapidly see the difference between that, which is a molecule of fructose, and at a glance you can see how different they are.
That's the great value of those things. You can see the difference without any effort at all.
Yes, that's right. But some models, of course, are just simply numbers, and many engineers will be designing buildings or bridges or jet engines, and all they see is a lot of numbers. They never see any real representation of what the final thing will actually look like.
Now, numbers to a lot of people means money, and I've heard the phrase somewhere, I'm sure, financial modelling. Is that where that connection lies?
Well, it's a very popular and common usage of modelling is to design a plan for your little company or even your large company. And we've set one up here which I think shows fairly clearly what the sort of things that can be done. We've got here the 4 quarters of the year looking into the future with his total, and it's a little computer shop. And the price of his computer, they're going down as we forecast computers go down in price. Right. Here is sales in numbers. They're multiplied together to give his revenue, so he's got his total sales there. His costs are on that line, costs of his computers, costs of his staff and so on. Yes. And he ends up with a profit. But he does have an overdraft, and he's using his profit along here to pay back his overdraft. And he gets down to about £15.93. So he goes along to the bank and says, that's my plan for next year. The bank manager says, I don't like that. You've got to wipe out that overdraft completely by the end of next year.
What a rotten bank manager.
So he says, well, how many computers have I got to sell to do that? And here is sold 98, and it's very easy to rerun it and calculate it. It's called goal seeking, to find out how many computers he's got to sell to eliminate his overdraft by the end of the year.
You're going to ask the question, what do I have to do to those figures to get the result, no overdraft?
That's right. Yes. I'll do that. I'll try. Well, it's beginning to print it out now, and you can see he's going to have to sell 105 computers this time, as opposed to 98 before, so he's got to sell another 7 computers, and that reduces his overdraft down to 0.
Mac, how does a model like this work, in fact?
Well, it's applying a set of rules. For example, when we talked about the revenue was equal to the price of those computers multiplied by the number we sold, and that is a little rule.
Now, although many computer models, like the financial ones, are used to find out what's likely to happen in the future, given the present circumstances, we sometimes want to discover just the reverse. We know how things turned out in the end, but how did it all happen?
Sooner or later, after every accident, the inevitable question, who was to blame? The drivers themselves find it very difficult to be objective about what happened, and even unbiased witnesses find it hard to estimate speed and distance. So how does one get at the truth? In the accident we've just simulated, sadly, the Ferrari driver was killed. So, as there were no witnesses, the only version of the events is given by that driver of the second car, the Escort. According to him, he was coming up to the junction with this main road. He stopped, made sure the road was clear, and pulled out, when suddenly, from out of nowhere, and travelling at least 80 miles an hour, came the Ferrari. The two vehicles met at this point here, but the force of the collision was such that they bounced off one another, span across the road, landing up a good distance apart. If we wanted to predict these final positions of the cars from their initial speeds and directions, it would be relatively simple. But what's needed here is just the reverse, to reconstruct the events that led up to the crash from the clues that are left behind. And that means modelling backwards. It's vital to know just how fast the two cars were travelling and what the drivers were really doing. And that's what accident investigator Tom Ravensdale must discover.
And there we have the complete data on the Ferrari.
So you've got all the vital statistics of the car now up on the screen. Where do we go from here?
Well, we now need to know what sort of speeds are involved, what was the Ferrari doing and what was the Escort doing. So we'll go into a program which tells us the speeds of each vehicle after impact. And we want the post-crash distance of vehicle 1, which is the emerging car, which was 37 feet. Post-crash distance of vehicle 2 was 46 feet. The coefficient of friction of the road, which is the slipperiness of it, was 0.7. We established that from a test at the scene of the accident. The angle of approach, now they approached each other at 90 degrees. Post-crash angle of vehicle 1 was 80 degrees, and of the other vehicle, 65 degrees. Now, here we have the speeds. The Ferrari at impact was doing 50 miles per hour.
Oh, that's a lot less than this.
Yes, it is, because he's not a witness. And the speed of the emergent vehicle was 21 miles per hour. The next question to ask is, could he have reached 20 miles an hour at impact if he stopped? Did he stop?
Mm-hmm. So, Tom, what about the Escort? Did he stop at that junction?
No, he didn't. He couldn't have stopped and then accelerated to 20 miles per hour and 20 feet. It's just not possible.
So what about his version of the events? Was he mistaken?
Well, it's certainly untrue, but he wasn't mistaken. No, I think he was lying, because from the angle of the crash and the speed, he must have been attempting to turn right, not left.
Jill Neville reporting. Now, Tom Ravensdale was using a perfectly ordinary home microcomputer to do his modelling on, so presumably we could do the same thing on our machine, could we, Mac?
Yes, we certainly could.
Well, I'm no great shakes at maths, so I hope it's nothing too harebrained and complicated.
Now, well, I really love those old Victorian puzzles, and we've got one for you. It's really nice. Yeah. You've got a pond in your garden, an ornamental fish pond, and in it is 500 gallons of water, some carp, and a leak. And it's leaking at 1/500th of whatever's in it every hour. At 100 gallons left, your carp are going to die. how long have they got?
Fantastic. It's like an O-level question, isn't it?
It's not an easy question to answer.
No.
And what we're going to do is create a little model, and we're going to graph it something like this. And along the bottom here, we've got the hours that it's got, up to 1,000 hours. We're graphing it in hundreds along the bottom, and the water in gallons, running up here, 500 gallons. So let's just have a look at the program. Well, there's the subroutine that we've done for the graph.
That, yes, go sub 800 means that at number 800 in the program, there is a subroutine which just draws that grid.
That's right.
With the markings, the number of gallons and the number of hours. Right. OK.
Now, here's a new one. Water equals 500. That's the 500 gallons of water that's in your ornamental fish pond to start off with.
Yeah.
And here we have one of these loops. For hours 0 to 1,000, we're going to draw our water. So for hour equals 0, hour here, we draw the point 0 and the water 500. So we draw the point 0, 500.
That's
now,
to make it draw that first point, which is actually on the line of 0 time. OK.
Now we've got to calculate the next point.
Yeah.
First of all, we calculate the leak. And the leak is equal to the water divided by 500.
That means 1/500th of the water.
That's right. That's the amount that's leaked away.
Yeah.
So the new water, the water that's left in the tank after that first hour, this new water here is equal to the old water, which was 500, minus the leak. Of course, this water was 500 here, so the leak in the first hour was 500 divided by 500, which is 1. Right. So the new water with 500 minus 1, which is 499. Then it goes back. It would plot that point, it goes back up here, and start to calculate for hour 1, and it will go through the whole routine 1,000 times.
Right. So the first calculation is quite straightforward. It's going to lose 1 gallon in 1 hour, isn't
That's
it?
right.
The next one is 499, and it's got to take a 500th of that and subtract it from 499.
Right.
And that's a great deal more complicated. It's actually getting into long division already.
Yeah.
And it's going to make how many of those sort of calculations?
Make 1,000 of those, yes.
Right. And it'll happen in seconds, I guess.
Well, we can do it. We just run it.
Right. Oh, there it's happening now. It's actually being calculated at this moment.
It's actually calculating at this moment.
Right.
And that's the point where you're going to die.
This is when we get down to 100 gallons of water, that's carp death.
But we can show it as this is not a representation of the pond. We can think in our imagination, we understand what's happening.
Yes.
But we can actually give you an idea of what it would look like in the pond itself. You see the time going down here, and the pond going out very quickly at first.
Very clever. Look out, 100 hours coming up. 100 gallons coming up.
And there it goes.
Goodbye, carp.
Goodbye, carp.
That's terrific. Now, I can see that with sort of 2 elements coming together for the calculation, it's relatively simple. But obviously in real life, in practice, it's never going to be quite as simple as that, is it?
Well, no, it isn't, because if it was real life, you'd have to take into account evaporation, and it might rain on the pond. You might have weed on the pond pressing it down, or not, as the case may be. Yeah. And you might even have a heron come along and eat your carp and allow the other ones to live longer, and so on and so forth.
So that's where computer power really comes into its own, is when you've got colossal amounts of data coming in to affect your final result.
Well, I think of it like the chess we were looking at the beginning. It's very easy to understand the rules, and in some of these models you can easily put the formulae together, but it's very difficult to know what emphasis to give to one particular set of rules and, how they interact with each other once you set your model going again.
Well, thanks, Mac. A very good example of a really big computer model which most of us consult every day is the weather forecast. Now, we may not always get exactly the right answer, but when you think of the size of the problem, it's surprising that we get any answer at all. The European Centre for Medium-Range Forecasting at Shinfield provides a 10-day forecast to all the EEC member countries. The problem with predicting weather is making a realistic model of how weather systems develop and evolve on a global basis, and then supplying that model with sufficient observations of what is actually happening around the world. The model is numerical, a series of differential equations based on how we think the atmosphere works. It must take account of the forces that control weather, gravity, pressure, and friction, as well as atmospheric variables like temperature, wind, and humidity. To predict what might happen in any one part of the world over 24 hours requires an enormous amount of calculation, and it would be quite impossible without a computer, unless, of course, you wanted tomorrow's forecast sometime next week. The Crays period of prediction covers the whole globe for 10 days ahead, and the number of calculations that it performs is over 530 billion. And here's the 10-day forecast, which is the result. You can see how the isobars change from day to day. What you can also see is the enormous area the forecast covers, which may help to explain why the model gets the overall pattern right, but isn't so good at telling you whether it's going to rain in Romford tomorrow. Bad luck, Romford. Well, games, models, simulations, they all seem to depend on the ability of the computer to apply the rules of the real world to the information held in its electronic imagination. But, Mac, where do the rules come from in the first place?
Well, some of them we know from the theories of physics and chemistry and mechanics. Some of them we can measure directly, but others we have to build a model ourselves, a physical model, and test it out. Right. And this is a model of a section of the roadway of the Humber Bridge, which was built for going into a wind tunnel to test various theories.
This is the actual wind tunnel model?
This is the actual wind tunnel model.
Without the chains or whatever they're called?
Without the
just the roadway
cables,
part.
That's right. And obviously on this you could check the wind flow. For example, here you've got wires as crash barriers. If you're using those solid Armco barriers, it would alter the wind flow across the surface. You've got these beautiful railings here. If you put something solid there, it could form different turbulence patterns.
And there's the sort of aerodynamic design underneath. It's all there in detail.
Yes.
Yeah.
But at the same time, they built a computer model for this. And then they checked the computer model against this, and of course they were different, and then they changed the computer model and changed this until they got them as near as they could to being similar. But once you've done that, you can use the computer itself and start doing these what-if questions. What if there's a traffic jam from end to end of the bridge and there's a 100-mile-an-hour gale? Does it fall over? You can take things to extremes, so there's a fair chance that the thing will stand up in the long run.
And miles cheaper.
Yes, of course, you can check it thousands of times for the cost of a bit of computer time, which is cheap.
Right. Thanks, Mac. Well, even if it's not 100% correct, a computer model does offer us a means of trying out a new design and testing it, as Mac said, to destruction without having to build it first. So the Humber Bridge stands a good chance of avoiding the fate of some of its more infamous ancestors. On a stormy night in December 1879, the Edinburgh Mail crashed off the Tay Bridge and into the Firth below. A combination of centrifugal forces on the curved part of the bridge and a gusting wind pushing the train further over was the likely cause of the disaster. William McGonagall takes up the story.
So the train slowly along the bridge of Tay until it was about midway. Then the central girders with a crash gave way, and down went the train and passengers into the Tay.
Nowadays, with the help of models such as the one used to test the new Humber Bridge, we no longer have to make quite so many guesses about the power of nature.